Honors Geometry, Note Section 13.5, Intersecting Chord Properties. Theorem 13.13. If two chords intersect in a circle, chord, chord, intersecting, then the products, that's multiplication, of the measures of the segments of the chords are equal. So, this is AE and this is ED. If you multiply each part of those chords together, that's saying that's going to equal BE times EC. It's pretty straightforward. Oh, we're asked to prove that this is true. Well, this is interesting. Given that segment AC and segment BD intersect at E, I got this jacked up. Boy, I have just made a bunch of mistakes on these notes recently. This should say, given that segment AD and BC intersect at E. That's better. Prove that AE times ED equals CE times EB. So we are proving this theorem right here. That's what we're doing. Well, let's start out with what's given. Segment AC and segment BD intersect at E. That's obviously given. If you look at this picture, what else can we infer? Well, wouldn't you agree that these two angles have to be congruent because of the vertical angle theorem? So let's jot that down. Angle AEB is congruent to angle CED. You know what? Before we do that, we should probably say those are vertical angles. Let's do that. How do we know those are vertical angles? Definition of vertical angles. So we can just look at the picture and tell. Then we can say that angle AEB is congruent to angle CED. A vertical angle theorem. Excellent. Let's see. Let's put these segments in. Wouldn't you agree that angle ABC and angle CDA have to be congruent? Angle ABE, ABE, if you will, is congruent to angle CDE. This is the theorem that we had in a previous section that doesn't have a name. Basically said that inscribed angles are congruent if they share an arc. So the arc that they share is this arc here. So this angle and this angle have to be the same. All right, we are cooking now. We could say that this triangle and this triangle are similar by the angle-angle similarity. Triangle AB is similar, cheesy poof. Triangle CDE by the angle-angle similarity. Left out some letters. Similarity. Now, if those are similar, let's see, 1, 2, 3, 4, 5. We could certainly say that AE over EB is equal to CE over ED. Now, if you're wondering, why would I write that? Well, at a certain point, we need to get AE, ED, CE, and EB into the problem, because they don't exist in this problem, only angles. So that's this side, and this side, and this side, and this side. I'm just trying to get into the problem. And because similar triangles means that corresponding sides are proportional, I can write this. So this is definition of similar triangles. Then, if I multiply both sides of the equation by both ED and EB, it gets rid of my fractions. That's the multiplication property of equality for real numbers.org. And that's what we were trying to prove. That's a tough proof, and I would hope that on a test or a quiz you would never be asked to do that, because that is rough. Theorem 13.14. If two secant segments excuse me, if two secant segments share the same endpoint in the exterior of a circle, which they do, then the product of one secant and its external segment is equal to the product of another secant and its external segment. So it's saying that the outside times the whole will equal this outside times the whole. So EC, the outside, times the whole segment EA should be equal to ED, the outside, times the whole segment EB. I think of it as out times whole equals out times whole. Special case. We like special cases. In this special case, the out is equal to the whole. So AB, outside, times the whole AC is going to equal AD, the outside, times AD, the whole. Out, whole, out, whole. Let's see if we can put this into practice. We have two chords intersecting inside the circle. According to Theorem 13.13, x times 2 should equal 3 times 4. So 2x is 12, that makes x 6. The units is centimeters, so centimeters. Similarly here, 12 times 3 should equal x times x. X times x equals 12 times 3, x squared equals 36. X is plus or minus 6. Talking about a length of a segment, x is 6 positive style centimeters. Here's another one. we got 3 times 7 should equal x times 5. That's 21 is 5x, so x is 21/5 of a centimeter. This is two secants intersecting on the external. Out times whole equals out times whole. This is 14 because 5 plus 9 is 14. This is x plus 6 because 6 plus x is x plus 6. So out times whole equals out times whole. Outside is 5, whole is 14. Outside is 6, whole is x plus 6. We're going to have to factor. Oh, no, we're not. I was wrong. 5 times 14 is 70. I was pretty excited. Distribute the 6, we get 6x plus 36. Subtract 36 from both sides, you get 34 6x. Divide both sides by 6, you get 34 sixths is x. That reduces to 17 thirds units of centimeters. 5. The whole is x plus 2. 2 times the whole. This is the special case. The outside and the whole are the same. So it'd be 2x plus 4 equals 36. 2x is 32. X is 16 units of centimeters. Let's see, these are both the same. They got one dash, so these are x. That means the whole is x plus x, which is 2x. So we got out times the whole equals out times the whole. That's 2x squared equals 4, which makes x squared is 2, which makes x plus or minus the square root of 2. This is the length of a segment, which is positive. The units we're using is centimeters. That concludes the notes for this section and the chapter. Please do the homework 13.5.